Central limit theorem is probably one of the most important result in statistics, if not mathematics. So what it say is that if I have a population X follow any distribution at all, it could be uniform, it could be bimodal, it could be skew left or skew right, doesn't matter, any distribution at all, right? With a defined mean mu and a population standard deviation sigma, and n is sufficiently large enough. Usually, how large enough? Usually, we use the sample size 25. Right? Then the possible sample means, this x bar here mean, this x bar here is possible sample mean is approximately normal at the same mean, mu, and sample standard deviation is equal to population standard deviation sigma divided by the square root of sample size n, right? So visually, it says this. So imagine I have a population pool. So this is my population pool, right? And within that population pool, I'm going to pick out a bunch of samples. So with size at least 25, right? So maybe I pick out sample 1, and then I'll pick out another samples, sample 2, sample 3, sample 4. Now, when I say sample and sample size, that means two different things. So in each sample, by the way, I'm going to, in each sample, there's 25 elements, right? So each sample have a sample size of 25, right? So sample 1 have a sample size of 25, sample 2 have a sample size of 25, and all the way to maybe, I'll take the samples of 1,000, and still have a sample size of 25, right? So what I'm going to do next is, for each of these samples, I'm going to average them, right? So for sample 1, I'm going to take an average of a sample 1. So I have x bar 1. For same thing for sample 2, I'm going to take the average of sample 2. So I have x bar 2. I'm going to take an average of sample 3. So I have x bar 3. Average of sample 4, x bar 4, all the way to a sample 1,000. So here I take an average of sample thousands. Right. And what I'm going to do next is I'm going to plot the average on the number line. So imagine I have a number line. And so maybe the average of a sample 1 in blue there, maybe it's here. The average of a sample 2 maybe it's here. The average of a sample number 3 maybe it's here. Average of sample number 4 maybe it's here, right? And I'm having 1,000 of these dots, right? 1,000 of these samples. So I'm going to do it 1,000 times on this number line, right? 1,000 times on this number line. And as you can see, over time, as I keep plotting the samples average of a size 25, I'm going to see something that looks very close to the normal curve. And that's what is the central limit theorem say, right? So as so as sample size, and it's better yet, as sample size get bigger and bigger, the curve going to get narrow and narrow, and your sample mean will get closer and closer to the population mean. Right? So if I increase my sample size, now instead of having a sample size of 25, I'm going to have like 40 or 50 or even 100. So as n sample size increase, the normal curve going to get narrower and narrower, get skinnier and skinnier like that. So that, oops, no, just that. Let's keep doing that. Like that. So that the sample mean will get closer and closer to the population mean. And the standard deviation get smaller and smaller. So let's take a look at an example of how to apply the central limit theorem. Okay, so waiting times for an order at Starbucks for all drive-through customers in the US have a uniform distribution from 3 minutes to 11 minutes with the mean 7 minutes. So I have this uniform distribution here with the mean is at 7 minutes and a standard deviation is 2.3 minutes. So this is the population distribution of a drive-through waiting time at Starbucks. A random sample of 40 Starbucks, so 40, I have n equal 40, a random sample of 40 Starbucks drive-through customers will be selected and average waiting time to receive their orders will be calculated. What distribution would you use to find the approximate probability that the average waiting time to receive their order for the 40 randomly selected Starbucks drive-through customers is at small 8 minutes? So there are two things they want us to answer here. Number one, they want to know what kind of distribution would you use to calculate the probability that the average waiting times is at most 8 minutes. Second is they want you to figure out what is the probability of the waiting time is at most, which is less than or equal to 8 minutes. So here I draw the graph for you where, so the starting time is 3, and then to 11 minutes, the mean is 7, standard deviation is 2.3, the density is 1 over b minus a, which is 1 over 11 minus 3, which is 1 over 8. Right? And x on the x-axis, it represents the time waiting for drive-through Starbucks order in minutes. So we're taking a random sample of size 40. So we are taking a random sample of size n equal 40. And then x is follow a uniform distribution at mu 7 and a population standard deviation at 2.3. So according to a central limit theorem, CLT here, we can say that x bar is approximately, maybe I should go down here. X bar is approximately normal at the same mean, mu equals 7, and the sample standard deviation is equal to sigma divided by square root of n, right? And sigma here is 2.3, the square root of n is square root of 40, so that will be equal to 0.3637. Okay, close parenthesis. So, so the distribution we're going to use here is the normal distribution according to CLT. Question number 2, we want to figure out what is the probability of an average waiting time is at most 8 minutes. Okay, so in order to find the probability, we need to find the z-score first. So z-score is equal to, remember the formula is observed minus the mean divided by standard deviation, right? Or in notation it'll be x minus x bar divided by s. Okay. So x here, my observed is a. Okay, my observed is a. My mean is 7, right? Here's your mean 7 divided by standard deviation, which is 2.3. 8 minus 7 divided by 2.3 is equal to 2.75. So my z-score is 2.75. And what you can do next is you can either look up on table what is the probability of a z-score of 2.75, or let me show you how to use technology to figure out the probability. I'm going to use an app here. It's called Shiny app. Shiny app. So my selected distribution is standard normal. Okay. Alternative hypothesis is less than, because we have px is less than or equal to 8. My statistic value is the z-score, which is 2.75. Okay, so as you can see, the probability is equal to 0.997. So according to Shiny app, my p-value is, if x is less than or equal to 8, is equal to 0.997. And that is our final answer.